Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 18th, 2026, just yesterday. It introduces a strategy that allows large language model agents to rationally balance the cost of gathering more information against the risk of making a mistake, achieving a 94% optimal match rate on decision tasks where standard baselines failed completely. The paper is titled Calibrate-Then-Act, Cost-Aware Exploration in LLM Agents. And as we'll see later, the implications for building efficient, cost-sensitive agents are quite significant. To visualize this trade-off, Figure 1 presents two scenarios for a coding agent. On the left, the diagram shows a guess-and-go strategy where the model is 99% confident about a standard CSV file, so it acts immediately. In contrast, the right side illustrates deliberate testing. Here, the agent encounters an ambiguous file, feels only 50% sure, and effectively decides to pay the cost of running intermediate checks before committing to a final answer. Well, Figure 2 outlines exactly how the authors structure this capability. On the left, the standard baseline agent operates in a typical loop. It receives a query and acts based on implicit confidence, which is often unreliable for complex trade-offs. In contrast, the right side introduces the Calibrate-Then-Act framework. Here, the workflow adds a crucial preliminary step where it estimates prior probabilities from the data. This explicit estimate is then passed into the decision loop, enabling the agent to reason mathematically about the value of further exploration. Alright, Figure 2 detailed the framework, and now Table 1 puts it to the test on a synthetic benchmark called Pandora's box. In this setup, the agent must decide which boxes to open to maximize reward. The middle rows show that standard prompted models, labeled prompted NT and prompted, fail to find the optimal strategy, maxing out at a 23% match rate. But look at the final row for CTA prompted. With both explicit priors and reasoning enabled, performance surges to 94%, nearly matching the theoretical oracle shown at the top. So, while Table 1 proved the concept on a synthetic task, Table 2 expands this logic to real-world domains. It presents a unified formalization mapping the same cost-aware process across three settings: Pandora, question answering, and coding. For QA, the latent variables track answer probabilities, where the cost is simply retrieval latency. Then, in the coding task, the setup is more complex. The agent must infer file attributes like delimiters, weighing the cost of unit tests against the risk of committing to buggy code. Okay, following that formalization, Table 3 presents the specific results for the question answering domain. The critical metric here is the discounted reward column, which balances answer correctness against the cost of retrieving extra information. First, the single-turn baselines illustrate the dilemma. Never retrieve is efficient, but inaccurate, while always retrieve maximizes accuracy, but suffers a low reward because of the high cost. Moving to the multi-turn agent section, CTA prompted finds the optimal middle ground. By choosing to retrieve only about 65% of the time, it secures the highest overall reward of 0.293. Well, having looked at question answering results, Table 4 now examines performance on the coding task, averaged across various cost settings. Here, the columns track the number of turns, unit test calls, and final discounted reward. In the top section without training, CTA prompted achieves a reward of 0.24, outperforming the standard baseline. Then, looking at the bottom section, we see that reinforcement learning boosts both approaches. However, the CTA version still comes out on top with a reward of 0.268, confirming that explicit priors help the agent generalize better than end-to-end training alone. Wrapping up, two takeaways stand out. Explicitly providing priors enables agents to balance exploration costs against risks rationally, and this strategy often outperforms end-to-end reinforcement learning. The broader implication is that building cost-efficient agents requires decoupling uncertainty estimation from action, rather than relying on implicit learning alone. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.